This lecture is going to talk about conjugated systems. And we'll talk about orbital symmetry and ultraviolet spectroscopy. This is conjugated systems. You have to be able to recognize, you could also say classify, whether a molecule has conjugated double bonds or whether they're isolated double bonds. And I will show you some graphs and some data that show that the conjugated double bonds and the conjugated systems have a lower thermodynamic energy stability. And then we'll talk about a few reactions in this chapter. We'll talk about, you'll do catalytic hydrogenation. And in catalytic hydrogenation, that is the experimental reactions that give you the information to rank that lower thermodynamic stability of the conjugated systems. Another reaction will be the addition of HBr to alkenes. And we will talk about a concept called kinetic versus thermodynamic property, or the product. So we'll talk about the difference between a kinetic reaction versus a thermodynamic reaction that's driven, and you get different products. So that'll be another reaction that you'll need to know for this chapter. We'll also talk about the allylic system. So we'll talk about allylic bromination. And you've seen these reactions before. All of these are review, but we'll talk about the NBS addition of the bromine radical to the allylic system. So those will be the three reactions we talk about in this chapter, in this section. And then also I want to just explain to you the concept of UV spectroscopy. And I want to explain this to you in terms of orbitals. So we're going to talk about a thing called Homo and Lumo orbitals. Homo is the highest occupied molecular orbital. Lumo is the lowest unoccupied molecular orbital. And we'll talk about some spectroscopy transitions that cause UV spectroscopy. What we will not talk about in this section, but is in this chapter, and we'll also be doing Pogel activity 18, and that's the Diels-Alder reaction, and that will be a separate video. So let's go ahead and start talking about classifying a compound, whether it's conjugated double bonds or isolated. So it's very important to be able to recognize if you have a conjugated system. So if I put these on the board, could you classify either as conjugated or isolated double bonds? Can we all agree that they all have double bonds, these compounds? Now, what I do is I do my hybridization. So you have this carbon here, and it has two hydrogens. So just a review of hybridization there. That carbon is bonded to 1, 2, 3 things, so it's sp2. This carbon, if you put in the hydrogen, is bonded to 1, 2, 3, that's sp2. This carbon, you can put the hydrogen in and see that's sp2. This carbon has two bonds, so it has two hydrogens. 1, 2, 3, that's sp2. So if you have sp2, 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 it is a conjugated system. So conjugated bonds, double bonds, are separated by one single bond. And you can see the single bond here. So that's the definition. I just noticed that everything's sp2. Okay, if you come here, this is sp2, this is sp2, but this carbon here has 2 hydrogens and it has 1, 2, 3, 4 things, so that's sp3. And then you have sp2 and sp2. So you see that there's an sp3 carbon in between those sp2 carbons. This means that these are isolated double bonds. And they're going to do slightly different chemistry from the standpoint it's not conjugated. All right, what about this one? This has just one single double bond. So you could say this is an isolated double bond. This one here, sp2, sp2. This carbon has 2 hydrogens, right? So that's sp3. So that would be isolated. This one, sp2, 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 sp2. So we have the sp2 all together. You see that the double bond is separated by one single bond. This is in fact conjugated. This is benzene, and we will be talking about this compound next chapter and maybe the next 2 chapters. So each one of these carbons has a hydrogen, and each one of these are sp2 carbons. So those would be a conjugated system. Now the reason why conjugation is important, studies have shown that if you do this catalytic hydrogenation reaction, so this is, let's see, how would we name this? 1, 3 pentadiene. There are 5 carbons, 1, 2, 3, 4, 5, and you react hydrogen gas on palladium carbon, you get the alkane. And this is an exothermic reaction, so that means it has a negative delta H and associated with it. So there's going to be some amount of heat of hydrogenation that's given off. So if you do this reaction, this is actually, in your book, you can see it's negative 225 kilojoules. And if you do this reaction with, let's say, penta 1-ene, so if it only has one double bond, and you take it all the way down to the alkane, that delta H will be a negative 126 kilojoules. Now let's do, this is conjugated. This is just a single double bond. Now let's look if we do an isolated. So this is an isolated double bond. And if you take that all the way down to the alkane, that delta H is the isolated. Is negative 252 kilojoules. Okay, so this is actually more stable. It only takes 200 and it gives up 225 kilojoules, where this one's 252. So you're looking at about 27 kilojoules more stable, having a conjugated system when you're comparing that with an isolated. You have an excellent slide in your book, and it's called Relative Stabilities. And it's really nice because it shows you a graph of increasing energy, and then you're comparing the different alkanes. So you're looking at pentane or a hexane. And each one of these compounds have undergone catalytic hydrogenation. So this is a cumulated diene, and this gives off 292 kilojoules. If you have a pentyne, so if you take a pentyne, which is an alkyne, and you take this all the way down to the pentane, this gives off 291 kilojoules. And then you can go for an internal pentyne. But let's just go down here and look at the isolated, which is 252 kilojoules. And then you have the conjugated, which is 225 kilojoules. And I just want you to see this graphically, because sometimes you will get graphs and stuff with sapling. But you see that what's happening is the starting energies are higher. Okay, because they're going to the same product. They're all going to the pentane. So the final product has the same energy. So the difference in energy is this difference here that's reported. And you can see that the starting energy of the compound is a lot lower. And so these conjugated systems start at a lower energy. And so you gain energy in conjugation. Now what's happening is in the structure of a conjugated system is, so here we have buta-1,3-diene. The double bond has, so an sp2, this is sp2, sp2, sp2. This has more S character, so 33% S character. And so it gets shorter and stronger. Shorter and stronger than an sp3, which is 25% S character. The S, the spherical portion of this covalent bond, is closer to the nucleus, and it brings them together. So you have more overlap, and you get this stability. Now, what's happening on a molecular orbital concept is if you look at a molecular orbital diagram. So let's look at MO, which is molecular orbital diagram of, let's do the butadiene. And I want to show you how to do this. So basically you have 4 carbons, and what I'm doing here is I'm showing you that these are sp2. So if it's sp2, each one of these has, each carbon associated with it has an unhybridized p orbital. And the unhybridized p orbital is where these pi electrons are able to reside. And so if you have something like this, then you increase energy. So if you're going to do a molecular orbital diagram of butadiene, this is buta-1,3-diene, then you start with this energy here, and a lot of times you just draw a line here, and you draw your 4 unhybridized orbitals here. Now, how many carbons do you have? You have 4. So you're going to have 4 here, 4 unhybridized p orbitals, and we have, what's our number of pi? Number of pi electrons. And you're going to have to get used to counting number of pi electrons in the next chapter. So number of pi electrons, you have 1, 2, 3, 4. So you have 4 pi electrons. Now energy increases as we go up. And so when you have 4 pi electrons, we have to put the 4 pi electrons in the orbitals. So you've probably seen like little boxes like this. And these boxes in general chem, you do Hund's rule, or Pauline's rule, Hund's rule, where you put your electrons in 1, 2, 3, 4. Okay, so you have 4 pi electrons, and you go an off-off principle as well. So you fill in the lower energy orbitals for your electrons. And each orbital can have 2 electrons. Now what this is, these are bonding. So these are pi bonds, so they'd be pi 1 and pi 2. And then this is an anti-bonding. So this, everything under here is bonding. And then this is anti-bonding. And you have to have as many anti-bonding orbitals as you have bonding. It's just a quantum electron principle fact. Okay, so if we have 2 bonding, then we have to have 2 anti-bonding. And you represent the anti-bonding with stars. Now, if you put in, this is the way it works, if you put in electrons in the anti-bonding orbitals are destabilizing. And this will make a compound not stable. But electrons in the bonding orbitals are lower in energy. And so that would be a representation of a molecular orbital diagram for butadiene. And then you would ask, are there any electrons in the anti-bonding orbitals? No. So therefore this is stable. So butadiene is a stable molecule. If we do so this has UV absorption. So what happens with UV absorption is then you have ultraviolet radiation. So what is the electromagnetic spectrum? The electromagnetic spectrum, we have the visible. So you're seeing yellow, right? We have Roy G. Biv. And then you have before red, you have IR. We've talked about IR spectroscopy. And then beyond violet. So V is violet, right? So this is our violet. So beyond that, you have UV. So this is a UV. And if you send this UV wavelength here, so if you send a UV wavelength, certain wavelength here, to this molecule and you bombard it, what you do is you promote one of these electrons. So you will promote one of these electrons from this orbital to this orbital. Okay, so you're bombarding this with the ultraviolet radiation. You bombard this electron, and the electron goes from this orbital. This orbital has a name. It's called the Homo orbital. That's highest occupied molecular orbital. And it promotes to this orbital, which is called the Lumo. And that's the lowest unoccupied molecular orbital. Now what happens when you take this UV energy away, then that electron will relax back down. And what the spectroscopy, the spectrum you're seeing, is this energy gap between your HOMO and your LUMO. orbitals. Now, if you get something like hexa 1, 3, 1, 2, 3, 5 triene, and you've got how many pi electrons? 1, 2, 3, 4, 5, 6 pi electrons. And you do its molecular orbital. So this is your energy. This is a molecular orbital energy diagram. And you do your 6. We'll do all of these. You got 6 carbons. And so, and then you do 6, you do 3 here. Okay, so, and they should be all equal. So this is just a bit, there's your bonding, and your anti-bonding. Anti-bonding at the top because it's higher in energy. And you have pi 1, pi 2, pi 3, pi 4 anti-bonding, pi 5 anti-bonding, pi 6 anti-bonding. Now you've got 6 electrons, so you're going to go 1, 2, 3, 4, 5, 6. Okay, this is your HOMO, highest occupied molecular orbital. This is your LUMO. So if you bombard this with UV ray, UV energy, a certain wavelength, this one electron will get promoted from the HOMO to the LUMO. And then this will relax back down and come back to the HOMO. And now what's happening here with increased in conjugation, so if you have increased conjugation, you decrease your HOMO LUMO energy gap. So you're going to decrease this gap here. And by decreasing that gap, that's where you can get different spectroscopy values. And in fact, you can look at one of your slides and you can see that hexatriene resonates at a 258 nanometer wavelength. It absorbs UV at that low wavelength, whereas the butadiene absorbs at 217 nanometer. So you increase that. So if you increase the conjugation, you also increase the wavelength at which you can get UV absorption. Now, let's go back to our electromagnetic spectrum. You have Roy G. Biv. This is the ultraviolet, UV. This is infrared. Remember when we have functional groups. Now, you take beta-carotene. Have you ever seen beta-carotene? Have you ever had beta-carotene's what you would find in a carrot? And I'm going to give you the structure of beta-carotene. All right, so this is beta-carotene. And if you look at each one of these carbons, they're all sp2 carbons. So how many conjugations do you have? I'm not going to count them, but you can see that significantly more than hexatriene. Well, what's the absorption here? This absorbs at 454 nanometers of wavelength, beta-carotene. And that's why it reflects orange. So it'll absorb blue wavelength and it will reflect orange. So we're getting, with more conjugation, we're actually getting into the visible wavelength. And that is how organic compounds have color. Okay, so some of the things we were going to talk about this chapter were conjugation. So hopefully now you can look at a organic compound and assign sp2, 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 sp2 carbons and realize that you have conjugated double bonds versus isolated double bonds. Hopefully that you can understand that the more conjugation, the lower the thermodynamic stability, the lower the energy is at room temperature, and um, and then you can understand how UV spectroscopy works by promoting electron from the HOMO to the LUMO orbital. There's a few reactions that I wanted to discuss in this chapter. Okay, so we said in our reactions that we would talk about catalytic hydrogenation, which we did because that's in order to determine the stability. But we also said we were going to take HBr, which is electrophilic addition, to a conjugated system, conjugated alkene. So we're going to do that, and we're going to talk about the difference between kinetic and thermodynamic control of a reaction. And then the other one I wanted to talk about was the allylic position. And we've kind of talked about that in Organic 1, but we're going to do, so here's your allylic position. It says sp3 carbon next door next to an sp2 carbon. So here's your sp2. And so the allylic is stabilized. So if you have an allylic radical, which you do with MBS. So if you react this with NBS, which is called N-bromo succinimide, and that structure looks like this. So here's an imide. An imide is a nitrogen in between two carbonyls, and that's N-bromo succinimide. Now what happens with N-bromo succinimide, with the presence of HBr, you get Br2, and you get just succinimide. And this is a small source of Br too. So when you hit this with UV, you don't have a whole lot of Br. And what happens is then you can do your normal free radical mechanism. And this is just a small source of Br. And so then when you hit that with HV, you generate your Br radical. And what's nice about that, then you can do your propagation step. So you put your allylic hydrogen there and your Br radical, and then you can show your fishhook arrows. You have 3 of them, and you get an allylic radical. It's very important that you show your resonance. Double-headed arrow, and you have 3 electron flow arrows. Okay, so you do have resonance with this because now you have an sp2, sp2, sp2. The allylic radical is an sp2 carbon. The radicals are sp2 carbons, and so they can participate in resonance. Then what happens here with the P2 is then you can, this would be your more stable free radical because it's a secondary allylic versus this is a primary allylic. And so then you can generate your BR. So if you add the Br Br, just like you do in propagation, then you keep generating a Br. So this is allylic bromination. This reaction is called allylic bromination, and you use MBS. Now, why is it important to use MBS? Well, if you just take Br2 and you have too much, so if you have a high concentration of that, you can remember that that made the bromonium ion, right? And then you have the bromonium nucleophile, the Br, will go and attack at the more hindered carbon, because that's a delta positive, and then you would get what we would call a heterolytic reaction. So this is a heterolytic reaction, and it would happen electrophilic addition. Addition will happen in the presence of lots of Br. Okay, so by using MBS, you're keeping the Br concentration down low, and then that gives you allylic bromination. Okay, but so you need to start using the allylic systems as starting material. And let's talk about now the HBr, kinetic versus thermodynamic control. Okay, so here's your reaction of 1, 3, 1, 2, 3, 4. So buta, 1, 3, diene. You need to recognize this is a conjugated system. Okay, because the conjugated systems can undergo resonance. So what happens here is you have a double bond, and it's going to get protonated in the presence of HBr. This is electrophilic addition. And now that hydrogen can either add to this carbon or this carbon. And you know it's going to add to the less substituted carbon, so you can generate the more substituted carbocation. And this is not just a regular carbocation, this is an allylic carbocation. So this is an allylic secondary carbocation. So what can happen now is you can get resonance. So these, because you got now this carbon's an sp2, this carbon's an sp2, and this carbon's an sp2. And so those electrons go there. And you also can get a primary allylic carbocation. Now, you also have the bromine radical. I mean, not bromine radical, the bromine anion. So this anion is now your nucleophile. And you know in the presence of a nucleophile, the nucleophile can either attack that carbocation, and you get bromine addition here, which is 3-bromo dash 1 butene, or you can get the bromine radical here, which gives you a product 1-bromo dash 2 butene. So you can get two different products. Now, if you look at your slides, you'll see that this is temperature dependent. So if you have negative 80 degrees, you're going to get the one, 2. This is the 1, 2 product. Okay, and the reason why it's called 1, 2 is because you would say 1, 2, 3, 4 when you see the conjugated system, and you'd say hydrogen adds to carbon number 1. So see, this is number 1, and then the nucleophile adds to carbon number 2. And so here's number 2. And you see that the carbon, so you got a 1, 2. So that's a 1, 2 product. And at negative 80 degrees, that's going to be 80% of your product. So this is at negative 80 degrees Celsius. Now, over here, this is carbon number 1, and the hydrogen added there. 2, 3. This is carbon number 4. So you got hydrogen here, that's a 1, and then bromine added to the carbon number 4. So they call this the 1,4 product. And the 1,4 product is your dominant product at 85% yield at warmer temperatures, 40 degrees Celsius. Well, okay, in Celsius terms, what is our room temperature? Our room temperature is 25 degrees Celsius. So this is slight heating, and you're going to get predominantly 85% yield of the 1,4 product. And that means to get the 1,4 product, what had to happen? You had to have your double bond moved in resonance. So graphically, what's happening? So energy increases here. This is your reaction coordinate. And we're going to start here. It's kind of a little different. We're going to start here with our intermediate. And our intermediate for this reaction is, well, this, which is the same thing as doing this. Okay, so it's showing you that this carbon's either here or this carbon is here. Okay, so these are your intermediates. You can do your resonance here on the intermediate. That's the valley. And then if you go up here, this is your more stable product. So hydrogen adds there and bromine adds there because this is the 1,4 product, and it's more stable because you have an internal carbon-carbon double bond. And if you go over, so that's your more stable. If you come here, you're going to have something less stable. Okay, so you can see your energies here versus your energy here, and this would be okay, so hydrogen adds there and bromine adds there. Okay, so this is your 1, 2 product. So you notice the hydrogen always adds on the 1, and then the question is, does your nucleophile add on the 2 or does it add on the 4? And this is less stable because the double bond is only mono-substituted, right? And this one's internal, this one's di-substituted. So that's why it's going to have a lower energy. Now, how do you use temperature to control this? Well, this has a higher energy. This is your transition state, and it has a higher activation energy, and that is higher. And so how do you get something to go higher? You increase the temperature. So if you increase it to 40 degrees Celsius, this will be thermodynamically controlled. So you'll get your more stable thermodynamic product. Now, if you do it at cold temperatures, you have a lower activation energy to overcome transition state there. And so at lower temperatures at -80, you can actually get your kinetic controlled product because this will form faster, but this one's more stable. And so that's energetically the concept of kinetic control versus thermodynamic control. So hopefully you're understanding that allylic systems offer us a more stable compounds because we have resonance, and then you also have the intermediate. Here, the intermediate for this reaction is an allylic carbocation. The allylic bromination with MBS would be an allylic radical. And so you want to do the resonance and choose the product for there. All right, so the next reaction that we need to discuss is Diels-Alder. And Diels-Alder reactions will be discussed during POGIL activity 18.